Welcome back. Today we'll discuss points and planes, or more generally, local versus global coordinate systems in a kind of environment, in this case, Grasshopper with Python. So let's check it out. Um, we can already see in Rhino that we have a global coordinate system by default. It's this XYZ Cartesian space, and we can actually recall that same plane by defining it in Grasshopper. So we can do plane, left click, set one plane, and X and Y, and we have the same global system here. Or we can also define using the plane tab under the vector category. We can have X, Y plane. This is the default plane, the same as the global space. And we also have two other global helper planes, which are this XZ and YZ. So these are just the same basic plane, but oriented so that the Z-axis is on Y for this plane and on X for this other one. So let's just see a little bit generically how you can define a plane or a Cartesian plane. So you can have an X-axis here. Let's say we have a Y-axis over here, and then we have a Z-axis which is perpendicular to the other two, and it's using the right hand rule. So if you go from X to Y with your hands, the thumb is pointing in the Z direction, so that's the right hand rule. So this means, if you recall the videos on vectors, that the Z vector is generated by doing the cross product of X and Y, and subsequently Y cross Z gives you X, and Z cross X gives you Y. So this is the basic representation. So whenever you want to define a plane, we can do it basically in two ways. Either we define the normal vector Z, and then the software will create the X and Y using default parameters, or a method I like more is we define X and Y and we get Z as a result. So let's see how to do that in Grasshopper. So let's delete this default planes, and let's create a new plane. So as I said, you can create it from the normal, so you can have the Z-axis and the origin. I don't like this methodology. I prefer to use this construct plane, which asks you the other two axes, so you can have more control over what's happening. So the origin is just a point 3D again. So let's create a point 3D to move it just so that it's not in the same position as the global origin. So let's do maybe 2 on X and 1 in Y. All right. And then we can change the X and Y axis by supplying vectors. So we can do X, Y, Z vectors. So let's say X is maybe a little rotated that way. So it could be 2, 1 as well. So 2 here and 1. And then this vector goes in the x-axis, and you can see the x-axis is now pointing in the same direction of this vector. Let's actually display this vector as well with vector display. So we'll use the origin as the anchor, and then we'll use the vector as a vector. And you see this is the x direction. So the same thing we can do. It doesn't matter if the vector is not unitized. This will unitize it automatically for you. So the plane has no concept of, well, it could have a concept of scaling, but it's not applied. So it doesn't matter the length of vector you supply. And then we define the y vector is actually defined by default. So you can see you have, in this case, the global y-axis. So you may ask why then the y-axis is pointing in that direction. Well, it's built so that it's always perpendicular to the x-axis, and it chooses the direction depending on the prevailing direction of the other vector. Let's see it in action so it's easier. So let's say we define a vector which is pointing towards us, so to the minus y space, so that you can see what I mean. So let's say we have -1 here in the y-axis, and this is the new y-axis. Check out what happens to the preview. You see the y vector now, it's in the opposite direction, and if you inspect, this is the y vector we supplied. So the x vector is the one that actually defines the main direction of the plane. The y-axis will just move accordingly using this this y vector, it doesn't matter if the y vector is not actually the real y. It just defines the plane in which the xy fall into. And we could do, let's say the max range is 1 here, and you can see that if you say 1, it goes in the other direction. If you say -1, it goes in this one. So now that we have this, let's create a more creative plane. Let's maybe say that x may be 0 and y it could be 1 and z could be 1 as well. So let's do this and this. So now this plane is slanted, so it's more interesting, and we can now inspect what the actual x, y, and z vectors are by deconstructing this plane. So if you go in here, you can deconstruct the plane we already created, and then if you go to origin here, you could go x, which is the one we defined, y, which is the one he calculated based on the y vector we gave, and then z is just a cross product of x times y, and it comes out in the screen direction in this case. All right, so now we define the plane, and by using this methodology, you can define whatever plane you want, even if you know the z-axis. I usually use this anyway. So from the z-axis and the x-axis that I want, I compute the y-axis using the cross product, and then so on. I use this one to define the plane anyway. So now we'll see how to get coordinates in this plane we just created of a new point. So let's create a point, any random point. Let's create it in Rhino, just because maybe here, and then we can move it up a little. Okay. So we have this new point, and we want to see, let's maybe move it a little bit here. Okay, we want to see what are the coordinates of this point, but not in the global space, but in this plane we just created. How do we do that? There's a specific component to do that called plane coordinates down here. So we need to supply the point. So let's get the point from Rhino. So there. And then we defined this system, and the local coordinate system is just the plane we created, which is this one. And now we get the coordinates, so it's 4.4, 4.4 almost again, and 1. Let's move it a little so it's not symmetric, maybe. Okay, there. So we have 1.7, 6.8, and 1.3. So as you see, like it's the coordinates x along this axis, the y along this one, and z along this one. Okay, so let's say now we want to get from the coordinates in a local system, we want to get back to the global. Of course, we already know in this case because we created the point by hand, but it may happen in other situations that you have these coordinates in the local system and you don't already know the global system, the global coordinates. So you want to get them. The way you do it is you go in the point menu instead of the vector, sorry, instead of plane. And there's this point-oriented component, which does the opposite of this plane coordinates one. So it takes a base plane in which the coordinates you supply are defined. So in this case, it's still our local plane. And then u, v, and w, which are just x, y, and z coordinates. So you just supply them, x, y, and z. And you see that we have 2, 5, and 6, which are the global coordinates of this point, which we can also inspect and check by deconstructing this point in this case, because we have it. And you'll see it's the same, and it's 2, 5, 6, 2, 5, 6. Okay, it's the same point in global coordinates. So let's now see how to do all this thing in Python as well, and then we can wrap up the episode. So let's call our usual Python script component, and we will put it here to the left. And then let's start. So we define a point. So let's maybe move it to the left here so we can use the same points and see that they are the same. So let's create a point P1. So P1, actually, let's import first. Import Rhino geometry as Rhino geometry. All right. And then we'll do P1 equals Rhino geometry point 3D. And this expects 3 coordinates, in our case 2, 1, and 0. And now we created the first point. We can also print it just to double check. Okay, print P1 there, and we can see in the terminal we have our string version of the point. Let's create another point P2 that equals actually the vectors. So vector V1, which is Rhino geometry vector 3D, and this vector 3D is just 2, 1, 0. And then let's see, we have vector 2, Rhino geometry vector 3D, and we have 0, 1, 1. Okay, so we defined our basic inputs, and now we can construct a plane. The way you construct a plane, we just do, let's say, PL equals, well, let's say, maybe, yeah, PL is fine, plane local equals Rhino geometry dot plane dot actually dot nothing. We open parentheses, so we call the plane constructor, and we supply the same inputs. We can have a bunch of ways to create a plane, as we can do in Grasshopper. We can either, well, supply another plane, so you just make a copy of it. You can put an origin and a vector, which is just a normal Z vector, which is the one I don't really like to use. And then we have this one, the third way to build it, which is using point 3D, X direction, and Y direction, which is the same as this construct plane. We'll use this this time. So we have P1, V1, and V2 as the parameters. And now if we print PL, we will see we get the characteristics of the plane, so the origin and the axis. This is not very nice, so let's preview it in Rhino so that it's easier. Where is my Rhino gone? Let me check here. Nope. Under here. Yeah. Okay. So we have our preview. So let's go back to here. So let's say PL. It's our plane. And now if we run it again, you see that this PL output is now displayed there. Let's just hide all this other stuff so that it doesn't get in our way. Okay. And indeed, this plane is the new one which we created in Python. Let's now accept an input, which will be our point. Let's call it our global point, global P. And then we do type hints. We can say it's a point 3D, and now we have access to this global point. And let's take the same one as before. Okay. And then we want to get the coordinates of this global point in the local plane, as we did before. The way we do it is we call a function plane, which is pl.remap to plane space, and this asks us the point. In this case, we called it global underscore p, and then this is just a local point. So let's call it local p. And we can print a local p, and indeed, actually, this plane remap function returns a tuple. So two things. One is true, so if the operation succeeded, and the other is a point 3D, which holds the coordinates of the local point. So we can do 1, so we guess just the point 3D which we care about. And indeed, it's 1.7, 6.8, y.3, which, if you recall, is the same we were getting before through this plane coordinates component, 1.78, 6.85, and 1.33. Okay, so we have seen this component as well. Let's check out this one. So point oriented. How do we do that in Python? It's pretty easy, actually. We already have the point, which is just our local p in this case. So we have local p x, y, and z. And we have a plane that is holding those coordinates. So we can do we can just call that plane, and on that plane we'll call a function which is plane at, point at, yeah. And then we supply uv and z in this case, which is uv and w, as we do outside. So what are these three parameters? Are just local p dot x, local p dot y, and local p dot z. Okay, so this will be a new point, global point. So let's call it maybe global p2, so, because we already have global p. And then if you print it again, we get, well, the same result as before. Let me just show you global P. They are just there's just a small numerical error. So in this case, you have 2, and this is 1.999. This is 5. This is 4.999. So it's just the same point, but within tolerance is the same point. Since the tolerance of the document it's set to, I believe, millimeters. Yeah, millimeters. This within millimeters is correct. It's the same number. So we're happy about that. Okay, so this was basically it. I'll just show you briefly the other categories you have here and describe them, but we won't see them in detail. These are just other ways to create the plane, but by using this one, you can do everything you can do with the other ones, other than probably plane fits, but we didn't care about that right now. And in the points menu, we saw this point oriented. You could define points which are in different coordinate systems, so not Cartesian, but polar or barycentric or cylindrical. But we'll see those when we need them in a practical example. No need to do much theory on it. And also these ones are more interesting seen in action on curves, so we won't deal with those today. So I hope this was useful to get an understanding of points and local versus global coordinate system in the Grasshopper and Python. If it was, leave a like, and see you next time.